Well, welcome, our second physics video. I'm going to change things up a little bit with this video. That last one, energy part one, it was okay, um, but it was inside. It's springtime. It's beautiful out. Uh, I wasn't super happy with it. It was it was kind of dull, not very exciting. I don't know. It was just lacking something, like a social studies class. I'm kidding. So I decided I'm going to switch things up. We're going to go outside. We'll do physics by the firewood. Here's a little tour. Well, here you can see the latest stack I've got. A little bit of cedar, some arbutus. Takes a long time to dry. Hopefully it'll be ready by the winter time. And here's an earlier stack. Lots more cedar. There's some arbutus, some old fir that I put. Anyway, time to get to some physics.
Well, here we are. You've had a little tour of the classroom today, and we're going to get started. So today, we're going to do just a couple of things. I'm just going to give you the bare minimum. On your first test back, you're going to have multiple choice as usual, and you're going to have two kinds of energy questions. And we're going to go through those two kinds of energy questions today, as well as a third question that you're going to see in some of your work this week. So let's begin. So two kinds of energy questions. So question type number one, add that in there for you. The question leads you to the answer step by step. So here we go. A 76 kilo cyclist goes off a 3-meter high jump at 15 meters a second. At his maximum height, he is traveling at 7 meters per second. Calculate the following. Kinetic energy. Well, we learned that last week. We know that kinetic energy is a half mv squared. So that's a half times 76 times 15 squared. We'll type that through our calculators. 0.5 times 76 times 15 squared is 8550. So if you're working on a test, that is, I don't know, 1 or 2 marks. Okay, next one, initial potential energy. Well, it says the jump is a 3-meter high jump, so we're going to go mgh. So that's 76 times 9.8 times 3. So we'll do that in our calculators. 76 times 9.8 times 3. And we get this number here, 2234.4 joules. Now, that's not our answer in terms of significant figures, but if I need it again, and I'm going to use the whole unrounded version. So here's the unrounded, or the rounded version to take as an answer. The total energy as he leaves the jump, well, he's got kinetic, he's got potential. We're going to add those two things together. So it's going to simply be 8550 plus 2234.4, and we'll type that in, and we get 10,784.4 joules. As an answer, we want 3 significant figures, so 10800 joules. There's my third answer. Okay, the next one. The kinetic energy at maximum height. So it says in the question, at his maximum height, he is traveling at 7 meters a second. Well, that's pretty easy to find. So half mv squared. So we'll go 0.5 times 76 times 7 squared. And I get 1862. And again, as an answer, it needs to be the 3 significant figures, and there we go there. Okay, the next one. The next one says, what's the potential energy at maximum height? Well, it doesn't tell you how high he was going, or how high he ended up going. Remember, if you're going off a bike jump, in case you're not sure, this isn't me, by the way. I go off bike jumps like that. This person would be going off kind of like that. So at this point here, the speed, 7 meters a second, and we're asked to find the height or the potential energy at that point there. And so what you're looking at here is you're looking at your kinetic energy is this number, but remember in part C, we found out the total energy was 10,800. And here's what I want you to be thinking. I want you to be thinking to yourself, if he's only got 1,860 joules of kinetic energy, but 10,800 altogether, where's the rest of it? And this is where you'd be thinking, well, the rest of it has to be somewhere and must be in potential energy. And so to figure out his EP at maximum height, we're going to subtract those two numbers. Well, we're going to subtract those two numbers because those are the unrounded ones. So that's going to be this, 10784.4, take away 1862, and we get, I'll just type it all in here, 10784.4 minus 1862 equals 8922.4. And again, as a proper answer, it needs to be 8920 joules. Now, we're going to find max height. Well, if I know the potential energy, pretty easy to find the height, so I'd say EP equals mgh, and I'd say 8922.4 equals m times 9.8 times height. And so we'll just work that out very quickly. You should have had lots of practice last week doing that. So 8922.4 divided by 76 times 9.8. And I get 11.98 meters. And that's going to turn into 12.0 meters. That's really high in the air. Definitely not me there. Okay, so the kinetic energy just before impact. And so again, you're thinking about what kinds of energy the cyclist has just before impact. So there's no height. That means there's no potential energy. There's no mention of friction. So that means all of your energy has to be kinetic. And so we're just going to use that energy up there. So 10800 joules. The velocity just before impact, well, I'm going to use this answer here and then calculate for velocity. Of course, we'll use the unrounded version. So we'll go EK equals a half mv squared. So we're going to go 10784.4 equals a half 76 v squared, and we'll just come up with our answer here. We get v squared is 284, 283.8, and we'll take the root of it to find v, and 16.8 meters per second. Okay, so on a test, the numbers would go like out of two marks, out of 1, because finding total energy is really easy, probably 2, probably 1 here, so 2, 4, 6, 8, 10. So these can be out of a whole bunch of marks, as you can see, and if you kind of keep your head about you, they're not too bad. Okay, so the next kind of question that you're going to have to do is one where you come up with your own equation. Now, over the years, I've ended up having to relent and give students this equation right here. It's not my favorite, but whatever. We do what we've got to do, especially in this case. So when you're thinking of energy, we want to think of the energy you start with, and then you want to think about where it goes. And so in our course, we're only ever going to be starting with kinetic and potential, and it can go into kinetic, potential, and thermal energy as well. So here we've got a 64 kilogram mascot. It's wearing a very furry suit, as you'd expect a mascot to do, I guess, and runs off a 12-meter high building at 8 meters a second. Probably not what you'd expect a mascot to do. On its descent, the mascot loses 1,800 joules of energy to friction. How fast is it traveling upon impact? I'm just looking past the camera because it sounds like there's a tractor going in the neighbor's yard. There is a tractor going in the neighbor's yard. I wonder what he's going to be thinking of right here. Can you hear the tractor? I didn't expect that. Anyway, we'll keep going here. Might have to wave at the neighbor. Don't want to be unneighborly. All right, let's think about the mascot. I hope you can hear me through this. So a 64 kilogram mascot. Well, he's on a building, and it's a 12-meter high building, so the mascot's got potential energy. So the mascot's got potential. The mascot is running, so the mascot has kinetic energy. And then as the mascot descends, he's losing potential, and you think to yourself, where is that potential energy going? Well, it's going into kinetic energy. It's also being converted into thermal energy because of friction. So we're going to have this, EK final plus thermal. Now, we say thermal energy and not heat. In physics, heat is a verb in that you heat something. Heat energy goes from cold to hot. No, goes from hot to cold. So here we go. So the potential energy, 64 times 9.8 times 12, plus kinetic energy, a half, 64 times 8 squared, into kinetic energy, a half, 64. Now I don't know the velocity, so that's going to be v squared plus 1800. He's fertilizing the field. This is round 2. So I'm going to figure out all of our numbers here. 64 times 9.8 times 12 plus a half times 64 times 8 squared. It's always best, people, to just let the calculator do the work. Here we go, 9574.4. It's not an answer, so I'm not concerned about rounding it. Let's subtract 1800 from both sides. We're going to get equals 32v squared. Divide by 32 and take the square root. At 13.7. So those are the two main questions, and you can see the difference between them. In the first one, we went all through step by step, thinking about things as we went. In this one, we think about the whole thing, what we start with and what we finish with. Okay, another one. This one's another important question, more of a multiple choice question, though the multiple choice question would stop after the first question. So here it is. If you can't read my scrawl, a 1,250 kilogram car is traveling at 90 kilometers an hour and skids to a stop in 57 meters. Find the force of friction between the tires and the road and the coefficient of friction. So there's several ways to do it. You could use Newton's laws if you wanted to. I think it's going to be best to use energy. It's much simpler. And so in terms of energy, you think to yourself, well, what kind of energy does the car have? Well, the car has kinetic energy, and so let's find that. EK is a half mv squared. We've got half 1250 times velocity. Well, I guess I better convert this. And remember, I said to you, to convert, you could do all the fancy stuff, but in physics, we often do kilometers an hour to meters a second. So we're just going to divide by 3.6, and I think we get like 25, which is why I picked 90 kilometers an hour, because I didn't want to deal with decimals. And here we go. So we've got this. Kinetic energy of the car is 0.5 times 1250 times 25 squared. And you're going to think possibly that the car has got, nope, not that. The car has got a huge amount of kinetic energy, and you're right. It does. It's a car. It should have lots. Okay, so that's how much energy it has. Now the brakes have to do work on the car to stop it. And you'd say, well, how much work do the brakes have to do? Well, the brakes have to get rid of the energy of the car, so the work the brakes do is equal to the kinetic energy of the car. If the brakes do this much work on the car, they're going to get rid of that much kinetic energy, which means the car is stopped. So the work then that the brakes have to do is this number. And from last lesson, you know that work is force times distance. So work here is force. I don't know the force. Oh, I do know the distance though. It's 57 meters. So we'll divide both sides by 57. And we'll find what force is. And we get a force of 6,853 newtons. Or as an answer, 6,850 newtons. Okay, the last part is, what's the coefficient of friction? Now, I can't remember how much of this we did. I think we did a little bit. Anyway, I'll show you here. On your formula sheets, you've got a formula that says this. The force of friction is mu times the normal force. Now, in Physics 11, the normal force is always just mg. So that turns into the force of friction is mu mg. And this is the coefficient of friction. So this right here is that little U-shaped symbol. I think I told you about it, but it's been so long now I can't remember. And it's great. We know everything else. We just found this. We know m from the question, and we know g is 9.8. So here we go. So 6,853 equals mu times m, which is 1250, times 9.8. 6,853 divided by 1250 times 9.8, close the bracket, and we get 0.559 as an answer. And that's the lesson. Okay, so on Instagram and on Office 365 Teams, I'm going to post two things. The first thing I'm going to post is a 2-question assignment that I want you to hand in. There's 2 questions, just like the 2 we looked at right now. And then the second thing I'm going to post is practice for you. I think there's 9 questions. It might say something in the title like April 9th, hand in, but don't. I'll make it really clear on there that I definitely don't want you to hand it in. And I'd like you to try your best on those ones as well. I'm going to wait a few days and I'll put the answers up for that one. I won't put the answers up for the first 2 questions for obvious reasons. Well, that's the end of the second installment of Physics by Firewood. I think we'll have to try something else next time. That was interesting, but I'm not sure I like the tractor coming through, or the crows, or the children playing next door. But such is life. Well, I hope you found this interesting. I hope you learned a couple of things, and I hope you're able to figure things out. And again, if not, please contact me through email or Instagram or Zoom if you want to set up a thing. We'll set up a class in the future for taking questions. Anyway, thank you.